basically we're going to cover why AI is not Quant 2.0, but it's something that really changes a lot of the ideas around quant investing. It's really a leap forward. What is actually something that the machine can learn and what it cannot learn in financial market. There's something to be said about that, which is really interesting. And then finally, reliable data for reliable results. We're going to focus on what is the most interesting data sets to be used and why is the case. And then finally, we'll have a Q&A session for everyone who's interested to pose some question, and you can do it by clicking, as I said before, on the Q&A button on top. So let's dive into what's the good part. We start from the good guys. So the good part is that AI is not Quant 2.0, as we said. Investing has definitely become a tech challenge. We've seen that as the internet has democratized information, everybody basically has access to the same level of information, and therefore to find that edge, technology does present a huge advantage. And this is why actually AI represents a leap forward, because it's able to elaborate on all this amount of data, but doing it very, very clever. And this animation that I'll show you in just a second tells you exactly that. Now, the square that you see here on the screen represent the financial market dynamics. So what we experience every day, basically. Now, our job as investor is whether it's discretionary quant, AI, it's to capture a little bit of that market that it is out there, a little bit of those dynamics to profit out of those. Now, you can definitely do it with a quant model or with an AI-driven model, but the difference is that as time passes by, we all know that market conditions do changes, and the best advantage, the leap forward is that these models are able to evolve and to learn autonomously, and we will see with the human guidance, but fully autonomously, the evolution and the changes of those dynamics. Whereas a quant model needs a human input to be fitting even in the most present scenario. So it tends to be a very good model that works in the past, but then when you go from time to time and as time goes past, it's really hard for them to adapt to new market dynamics. Now, first of all, why AI is not Quant 2.0? It's because we have to completely rethink the role of backtesting. Now, quant, which traditionally came out to bring the scientific method towards investing. If you can test it and prove it, then it means there is a dynamic behind it. But it heavily relied on backtesting as a method to develop a model. And effectively, what we represent here on this animation is basically, few possible parameter configuration that we call model 1, model 2, model 3. You analyze the performance in the past, and you choose basically what is most stable. And there are ways to do it scientifically. You can actually do in-sample analysis, and then you do out-of-sample analysis, cross-sample analysis. You test on other markets, for example, in the same period of time, or in a period where the model has never been developed on. But nonetheless, it heavily relies on the human input and on just finding the right combination of parameters in the past. Now, what AI allows us to do, if used properly, is actually to completely rethink the role of backtesting. And actually, if we think about the same parameter configuration, the same model that we call model N, the last one, they can actually be seen as a full surface. Now, what does this surface that it's coming to life now represent? The surface represents all the possible parameter configuration within that anomaly. So let's say that we're exploring momentum. Okay, momentum. So the inertia in prices and actually the inertia in returns. Now, what we find is that if parameter 3 is the return, okay, parameter 1 might be, I don't know, the look back period. So the period in which you look back to formulate your momentum factor. And parameter number 2 would be the holding period. So how much you keep that stock in your portfolio. We see that immediately what we can draw is a full surface that actually explore all the possible variables within a time span that it's not just 1 year, 6 months, of looking back an older period, but it's actually the full granularity of that anomaly. And that surface actually, if you think about it, truly captures the anomaly. Now, what we can tell immediately is that the point that we've seen in the backtesting before, which is the green point, is actually a point on an unstable surface, and therefore is an unstable portfolio. So what we have the fear about for that portfolio is that as time passes by, what might happen is actually not going to be there any longer. So even though the anomaly, the momentum effect is there, as you can see, the surface is always positive in period 1, period 2, period 3. On average, is always below 0, so it's above this grid underneath. So there is that anomaly. The optimum point decided by a developer, it's not really stable because the surface is unstable. So this is where actually AI, it's not Quant 2.0 any longer. And this is what we actually do. So effectively, what this animation shows you is how our team utilizes AI in the model development. The goal is not really to find the best parameter configuration in the past, absolutely not. The goal is to deconstruct the class completely, make it learn certain dynamics, and understand how the model interacts with those dynamics. With the goal of what? Of stabilizing the surface, so effectively stabilizing how the model catches that anomaly. And effectively, what is the goal of what's the added benefit of a stable surface? That with a stable surface, it doesn't really matter how much condition move around and market changes. You tend to be always kind of in the same area. So you would expect less shift of the factor that you're exploiting. Now, the added value on top of that is at the same time, if you have a stable surface, it's really easy for a machine to move around within this surface to find what, from time to time, what is the best place to position the values, which are still coherent with the investable principle and the investment goal that there is behind the strategy. Now, this is, in terms of the actual, applying the machine. But if we think about the role of human within the development of a strategy, that's already a different story altogether. So in a traditional quant model, there is a phase of data collection, which is very important. We're going to go through that in a minute. But then there is the human programming assumption. So there's a developer, someone, an analyst, someone who actually put assumptions within the model, test them with an hypothesis. The strategy gets developed, and it's obviously maintained constantly by a human. The problem, though, is that the human assumption tends to build biases and emotional within the final strategy. A good example of that, if you think about it, is if you're developing a model that aims to do, a macro model, you would think that, probably using GDP is a good idea of a country, of multiple countries. The moment you think using GDP is a good idea, the moment that you're making that decision, you're already interfering with the model by providing the data. And probably because it makes sense from a human standpoint, you would actually force, or there's a high risk that the developer would force the model to utilize that information. Whereas probably that information is already embedded in the data set somewhere. And this is actually where and why it's really interesting, the AI approach. And the AI approach comes from a completely different point. So it always starts with the data collection. This is given. But then the difference is that the human is not really working into developing the model. Yes, there is the bit which is putting together the neural networks. But then it's working on thinking and finding ways to train effectively the machine. Then the machine already develops the strategy by itself, supervised, we'll see in a minute. And then the model, the most interesting bit is that it is a continuous cycle. So it's a constant learning. The model is always having new information flowing in, and that information actually helps the model to be more effective as time passes by. So this is why, often, I get asked the question, but will, AI be better, 3 years from now? Yes, it will, but because of two things: R&D, so research and development in the field, and investment in computing. So that's really good. But the model itself will not be better. Will be better to fit the world that we will live in 3 years from now. So it's a matter of adaptability, and this is why human supervision is key. Because to think that these machines are evolving by themselves and learning by themselves is cool, but we need to have the human doing two things: making sure that the training input is spot on, and that the human supervision on the constant learning, on the continuous learning, is going smoothly, and the machine is actually not deviating from the principle on which has been trying to recover. Now we've seen, so that hopefully we touched briefly, but AI does really represent a leap forward. Now there's the bad thing, that it's not really a turnkey technology, and it can learn something, it cannot learn something. So first of all, AI, even though it's really cool, it's not something magical. It's just a tool. So to put it in perspective, everything has to begin with finance. And to understand why this is so important, we have to take a look at this, easy chart, which shows two things. It shows on the x-axis the model complexity. So the more complex over here, the less complex the model over here. On the vertical axis, the y-axis, is actually the error. Now this line shows the bias square. The bias square is the error that comes from erroneous assumption. So effectively, the simpler the model it is, the less the model it is to catch relevant dynamics. The more complex, the more the model is able to catch, effectively the dynamics. On the other side, we have the variance. So the variance is actually an error that happens on how the model is sensitive to the data that has been given in input. So the more complex the model, the more the model tends to be sensible to small changes in the data set. And this actually tends to lead to overfit. So we have underfit and overfit. The sum of the two is the total error. Now, this is why we call finding the sweet spot. And because at the two extreme, we have the two dynamics. The underfitting, so the model does not really catch the relevant relations, is just a line in the middle of a nebula of points. Whereas on the other side, the model is just actually learning noise. So there's no actually value on what it is learning. And this is why both models are not able to make reliable forecasts in the future, because they're not really developed with a good balance between a complexity of the model and on the same time and not going over in the over complexity. And this is why we find in the middle a good fit, a robust fit, which is something that passes through the individual points, but it's able to capture a certain dynamic and actually is able to learn what are really the intrinsic prosperity of that market phenomena. And this is what it's called generalization. So generalization is the most important thing, which is the ability to extract the essence of a concept based on examples. We can all say that these are trees, not because we've learned that this peculiar picture is a tree, but because we've learned the properties about it. A properly trained model is able to generalize, therefore is able to adapt and learn to new unseen data. Because at the end of the day, the whole concept of learning of a model is key to make sure that the model will be able to interpret correctly never seen information. And this is the most important thing. So finding the right balance. Now, the question is, what about us? Do humans overfit? Because we've seen that with machine, it's a matter of life or death for them to find the right balance. What about us? I do think that we do overfit as well. This is a nice picture I've seen it 1,000 of times, and each time I see faces where they're not really there. This is called pareidolia, which is a perception of a pattern where it's not really there. And if you think about it, in the financial market, how often do we see things in the pattern, in the data, where it's not really there? So as human, we do suffer the same thing as a machine. We just cope with them in a different way. So having understood, the two extreme of the spectrum, we can really, drill down in what the machine can learn and cannot learn. The machine can definitely recognize hidden pattern in data. and especially understand where the outliers are. So if there are anomalies, so it's really good at detecting anomalies. Second thing is it's really good at adapting and simulating scenarios. And this happens because with the proper modeling, it's not a linear modeling, so it's able to cope with the complexity of the market, whereas econometric, which is the instrument mostly used to develop quant model, struggles a little bit to cope with the complexity of the market. And it's really good for portfolio optimization goals because we'll see in a minute, it's a very highly vinculated and constrained portfolio and problem to solve, and therefore that's where having the chance to optimize for multiple buyers comes in handy. What it can definitely not do is predict a black swan. COVID-19 couldn't be predicted. 2008 crisis cannot be predicted, or time in the market. What it's interesting though is that it can definitely adapt to those changes. So a good model cannot and should not, I would stress that they should not predict the black swan, but should definitely, and you would expect that, understand on how to quickly understand on how to cope with the changes in market conditions. And this is key. This is the learning bit that we stress a lot, but that continuous learning is critical to making sure that your model is able to adapt as these massive changes in the market occur. Now, what we find to be one of the most successful spaces to apply AI is particularly in the portfolio construction, especially around the forecasting of variance and covariance and the return distribution over the next 1 to 3 months. The reason being that it's a very complex problem. Mathematically speaking, dealing with the variance and covariance metric is a complex problem, and the AI copes very well within complex dynamics. You should never, though, use AI to predict time series. So time series on AI, it's meaningless because it goes back to the pareidolia example. It tries to learn things that happened in the past, and that's just a mistake. So effectively, what we're doing and proving to have really good results is doing these two things at the same time. On one side, we work to forecast potential evolution within the variance and covariance matrix. And on the other side, we take into account the evolution and the structure of the return distribution of the element within the matrix, especially the left-hand side of the distribution. So the kind of the tail risk to evaluate the riskiness of this asset to be placed in the portfolio. And you use this, of course, to build the portfolio. More in details, the process that we use is structured like so. We start by a defined investable universe. We actually build thousands of matrices with different dimensions from the one in the past. So we decompose the past, we create matrices in the past with different dimensions, with different time span. Going back to that surface, we're able to utilize really the full time span and time horizon to build those examples. And then effectively what we do is we use this to build cluster. And then when we come in with the current scenario, we actually try to associate, or our machine tries to associate each cluster to areas within the variance and covariance matrix. And effectively, we use this to build the portfolio weights. So the changes happen over here. We're not using the variance and covariance matrix as a tool to be optimized, or as an object to be optimized. We're using the variance and covariance matrix as a describer of the world, because a describer of the market dynamics. And thus we, learning from the past, we try to recognize how different areas within this, describer of the market scenario today might evolve in the future. If we do it correctly, then effectively the portfolio tends to be a portfolio that is well balanced, because it's not optimized effectively for anything on the current scenario, but actually it's something that takes into account potential evolution in the future. Now, to conclude, we go into the ugly bit, the data. So there's no beating around the bush. It doesn't matter how fit you are. If you eat junk food, there's no chance you ever gonna win. And this concept is called garbage in, garbage out. It's a very known concept in machine learning in general. More than ever, because the machine is not really able to interpret the quality of the data that it's given. So a poorly trained model tends to be really, really dangerous because it cannot self-detect if the data quality is poor. So it's key to have two things. First of all, have a strong idea on where to find the data and having human to clean the data set, and then have systems to make sure that the data each time in the investment process, whether it is in the development phase or in the continuous learning, so as the model is attached to the market, always is filtered to make sure that there's no junk food going into the machine, because that's critical to have good results at the end. So we, throughout the years, we've experienced, working with many types of data, and we actually build a grid that, on one side has the predictive power of data, and on the other side has the predictive horizon of that data. Now we find that in the bottom left corner, we position the news and market sentiment. And this is, data that we feel that has really low predictive power. And if it has any, it's really on a very short time span. So there's that. Then we enter into the area of the alternative data. So the alternative data, it's like a bulk. Some do really add value, some other not so much. It's really hard sometimes to find the causality, to understand the causality. Is the price be moved by the data or the other way around? At the top right-hand corner, we find the company filings and fundamentals. We all know they have, good predictive powers, but the time horizon, is quite long-term. Whereas the historical market data, which means, every data which is structured, it's actually something that is undisputable, reliable. It fully reflects the market dynamic. If you think about it, the returns, often people, when you say historical market data, think about prices. It's really returns, and it's the derivatives of returns. So we go the variance, covariance, the distribution of the returns, and all the moments after that. And that is actually what, if you think about it, tells the whole picture of the market, define the micro and macro structure of the market. And then the other added value that partially embeds all the other data. This is why we use, in our models, solely historic market data after years of trying and failing. And that's where we find the most successful way also to clean and make sure that the data is always spot on clear, because you're just as good as your weakest data point. Don't ever forget that when we're talking about machine learning. So to conclude and open up for Q&A, given that we've reached the 25-minute mark, what is the takeaway of my presentation is that AI, it's something that is really adaptable to the complexity of the market. We've seen that econometrics and traditional backtesting is not really suited to understand even more today's market. It is not though magic, so we cannot expect to throw in AI within an investment process or just within a data set and expect the machine to learn something. It doesn't really work like that. It is just a tool, and everything begins with finance. Training the AI is a very delicate process, needs human supervision, and once again, the cleaning and the importance of the data is key to successful results. And finally, it can really improve the way we invest all together, because it leaves the human in a higher position, not really running the calculation, exploring all the possibility with all the the risk of incurring into the pareidolia anomaly that our brain is so good at catching, and actually leaves us in the position where we actually can think a little bit long term and think how to train the machine to catch more subtle anomalies in the data. So this is why we feel very confident to say that at the end of the day, between the good, the ugly, and the bad, the good is the one to prevail. And this actually concludes my presentation, and I'm happy to take any any question that you guys have given me. I already see 5. Should I pick them up?
It's up to you, Tommaso. If you prefer to take them yourself, or I can read them out.
Yeah, fantastic. I'll just have it open in front, so I'll go one after the other. Do all financial services deal with reflexivity? And let me see, because it's a continuous of the question before. Okay, so the question is that basically bridges continues to fall down in store, market crashes continue. What is the difference between using AI in engineering, materials, and financial markets? So it's completely a different story. If we think about what AI is a technique. It's not really let me simplify. AI is a kid who has a very brilliant kid who has 4 years of age. So he's not able to make any intelligent decision by himself, but he's able to make incredibly good calculation. So he can only do what someone else, what a teacher trains him to do. So to think that the same technique can be utilized in engineering or materials or in the financial market is not really the case, but it's the same concept. So a machine that is able to utilize information by itself. How you use it, though, it's a completely different story, and we have to be very very straightforward into starting by a known market dynamic, and then training the model to catch that, as time passes by. There's another question that says, where does the risk management fit into the process and how it is done? So the risk management fits at different level. There's a strong risk management that happens ahead of everything, which is actually ahead of the development of the strategy, which is checks, automated checks to making sure that the model does not learn things that we know those are mistakes. So that's key number one. Then when we go into the live application, so we've tested the models, we're confident and the model can run live. Then we go into the live training, and we have different level of risk management over there as well. There's a human layer which makes sure that and checks that the data quality is coherent. That's once again very very important, and utilizes parts are algos that do it automatically. Part is supervised by the human to make sure that the model is not getting junk food in. And then there is all hard-coded layer within the investment process to make sure that the model is coherent with the constraint that it's given. If we're talking about a multi-asset portfolio, might be sector exposure, volatility, liquidity, whatsoever. So there are coded checks over there. And then finally, there is for us, for example, there is a team dedicated, which is called mission control team, that actually makes sure that it's like, looking at the dashboard, make sure that the model is coherent with all these constraints. So there are multiple levels. Some are, human supervised, some are coded in the code, some other are actually human implemented. Tommaso, thanks for the fascinating presentation. This is Dan. A few questions. One, how do you avoid the issue you mentioned that occurs in the quant models where the human input forces the model to focus on a particular variable, GDP, include everything and let the machine choose? Well said. So Dan poses already has 3 questions, but I'll start with question number 1. Dan poses a really good question, which is I mentioned GDP as a variable that an analyst might be, forcing into the machine, whereas it's really good for the machine to deduct information. So there's a cool way to do it, which is using 2 different levels of artificial intelligence, or rather machine learning, whilst developing a model. One is using random forest. I'll go down in a second about that. And the other one is using neural network after that. So random forest is basically a type of machine learning algorithms that actually tries to split it. It's built out of the decision trees so how you formulate a decision, and actually tries to split the data set each time by moving around the variables. So the easiest example that I have in my mind is the game Guess Who, the one that you play when you're a kid, that basically you know what the faces that you've chosen, and you have to guess what your mate has chosen in front of you without looking at the picture and just asking questions. There are boys, girls, with sunglasses, not sunglasses whatsoever. So posing the right question is key to reaching the result, which is understanding what is the faces. And if you ask as a first question, is the picture that you've chosen someone with mustaches? It's not really such a good question, because actually it lowers so much the data set into 3 or 4 out of 100, which it does not really make sense. So the best question is it a boy or a girl? Because it allows you to really divide the sample into 2 great areas. So effectively, to put this into scale is what it's called doing a random forest. And using random forest to assess the quality of the variable is key. So we actually throw all the possible combination. We use a screen of random forest to understand if they add value. So mentioning the GDP. How do you infer if the GDP is contained into something else? If you run this, random forest for many iterations, you will find that, some variables are more important than others, and some are contained into another. Once we find that, then we take the quality one and we feed those into the neural network. So this is how we tackle. It was quite a long response, but quite a long answer. But the thing is, it's not that easy, and it's really 2 different steps. The second question that Dan poses was, are there any useful rules of thumb of data transformation that you really need to undertake before introducing the model? Yes, the rule of thumb for data transformation is try to normalize as much as we can. So to avoid giving the single data and actually normalize. This is rule of thumb number 1. Rule of thumb number 2 is shuffle the data. Don't ever try to to provide the data always in the same format, because the machine is so clever that it might learn the position of the data rather than the data itself. And to simplify, imagine that you've developed an AI and an artificial intelligence system able to detect a ball on a screen, but the example that you give is that the ball is always in the same areas on the screen, always on, in the bottom left corner. The problem is that when you give an example where the ball is not in that corner, probably the machine thinks is that in the corner because it has learned the position and not what the ball is. So always shuffle the data. Rule of thumb. Third question, how do you choose the number of layers in the neural network? A very good one. Once again, it goes down to the complexity. Do you remember the chart where we've seen before the two balance, which is this chart over here? It goes down to this one. How do you choose the number of layer? You basically have to dance between underfitting and overfitting. It takes experience, it takes trial and error. But the best thing is that to understand if a human is overfitting is tough. To understand if a machine is overfitting, it's quite easy. There's a lot of tests that you can run to make sure that you're right in the right balance. I have a lot of questions. I'm losing track. Okay, Yvonne, is it right to think that AI competitive edge lies in the speed in which it reacts to changing in the market dynamics? It recognizes pattern before other can catch up on it. Yes, the question is yes, but I will go a little bit one step forward, which is not just catching, because often when you think about catching, quickly a dynamic, people often think about trading, those fast algos that trade a lot, which is not really the case. Those are not the most clever algorithm. Those are the quickest. And to be the quickest, it doesn't mean to be that you're the most clever one, because a clever algorithm needs to have time to think. So effectively, the best advantage is that it's able to react quickly to cope with a different scenario. And for example, for us, to present a concrete example, the COVID crisis has been it's been tragic on one side, but it's been very, very good to test our models. And the best thing that, for example, we've seen how the model learned to completely change the asset allocation technique that was using before COVID and after COVID. And the thing is that a human being could have done that the same way, but imagine the amount of weeks and months that a quant team would have need to take the model, looked into it, look what the model was catching, find ways to optimize for the model, deploy the release of the new improvement in the code, and have the code trading again. That would take months. The model did it in a couple of weeks, and it just did something very, very clever, which was moving from a more in-depth allocation. So, for example, in the equity space, model that tends to work with variance and covariance focuses more on sectors rather than geography. During the COVID crisis, we actually saw something completely different. The model, never done it before, started allocating in geography rather than sectors, because the increasing noise on sector was making the prediction very unstable. And so it understood, of course, our team, mission control, was really monitoring very, very closely. But what was interesting that it was able to understand that taking such a strong bet into sectors with that level of volatility was too uncertain. And thus it completely changed the allocation technique and went to a more, I would say, strategic rather than tactical, or rather, strategic allocation, more geographic spread to balance it out. And now that we're kind of back into a more tranquil regime, some more normal regime, we're going back to the same old thing. So it's really good to see that evolution happening, and it takes just a couple of weeks. That one.
Tommaso, we are just coming up to time now, so I think that would probably be a good point to wrap it up.
Yeah, fantastic. Yeah. I would then thank you all. I see that there are still a lot of questions to be asked. I'll make sure that we're gonna get back to you with all the answer for those questions. And if you have any more, please write us at ask@m.m that you see on the screen. We're happy to have our team get back to you with all the questions replied. Thank you very much for having me.
Thank you again. That was a really, really interesting presentation, and I can see that had some really great questions come in. And also sorry to those of you who we didn't get to your questions. I have seen that there's been a couple of people asking whether the recording will be sent out or anything. So typically all the webinars do get uploaded to CFA UK Discover. So you'll be able to log in there later this week and come back to the recording. So yeah, thanks again, Tommaso, and thanks everyone for coming. Looking forward to seeing you again in the next webinar.
Thank you all. Bye-bye.